Okay, this video is going to serve as a review for all the stuff I think you need to know before we get into the real dynamics videos. All right, so let's just start. So a scalar. What is a scalar? A scalar is a quantity that only requires a magnitude. So something like distance is a scalar. You know, how far away are you? 10 feet. How fast are you going? Speed is a scalar. How fast are you going? 10 miles an hour. A vector, on the other hand, is a quantity that requires both magnitude and direction. So it needs magnitude and direction. So displacement, you know, I'm 30 miles away due north, right? Before, we just said we were only, 30 miles away, but where? What direction? I'm 30 miles away due north. Now it's a vector, right? Velocity. How fast are you going? I'm going 75 miles an hour east down the highway, right? That east is a direction component, right? So that turns it into a vector. So we'll be working with these 3D vectors, mostly. And a vector has two components. It has a scalar component, which is A1 in this case, A2, and A3. Those are the scalar components, or the distance components. And then we have these direction components, which are this I hat, J hat, and K hat. So let's talk about some of the notation here. I do my vectors. I denote a vector with an underbar. With that underbar, some books do it in bold. I can't write in bold. Some books have this like arrow thing above the vector. I don't do that. I was taught underbar, and I'm stubborn, and I'm sticking with underbar. The little hat above our unit vectors, well, okay, I just gave it away. It means unit vector. The little hat above it means unit vector, and unit vector means that the vector is of length 1, right? So I hat is of length 1, J hat, that's length 1, K hat, that's length 1, right? And those denote your directions. Okay, and these have a special name. This I hat, J hat, and K have a special name. They're called the unit basis vectors, the orthonormal unit basis vectors. So let's break down that word. What does ortho mean? Ortho means orthogonal, or they form right angles with respect to each other, right? So I hat forms a right angle with J hat, and I hat also forms a right angle with K hat, and J forms a right angle with I and K, and then K forms a right angle with I and J, right? So this kind of makes your coordinate system. And then normal means unit length, and I just said unit length means length 1. So all of these are length 1, length 1, length 1. And so the way we can think about how this vector capital A is constructed, it goes A1 in the I hat direction, then it goes A2 in the J hat direction, then it goes A3 in the K hat direction. So if we go to our little graph over here, we go A1 in the I hat direction, then we go A2 in the J hat direction, and then we go A3 in the K hat direction. You can see if we follow that path we just did, we get to the tip of vector A, and we've defined our vector A. So note, we'll talk about the differences between a reference frame and a coordinate system another time. Just know that we define our coordinate system with 3 mutually perpendicular unit vectors. All right, so that's a vector. The magnitude, or the length of a vector, is given as the following. So the notation are these like double vertical bars surrounding the vector, and the magnitude of a vector is equal to the square root of a vector dotted with itself. And we'll talk about what a dot product is in a second. And this gives you a scalar quantity. This just gives you a number. You can construct a unit vector. You can construct a unit vector by taking the vector and dividing it by the magnitude of itself, right? And I kind of think of that as you're eliminating the the length component of the vector, and you're only keeping the directionality component, right? So I have this long red vector A defined here, and if I divide it by the magnitude of itself, well, I get a vector of length 1 pointing in the same direction as, or is parallel to, the red vector, right? And so now I'm left with this A hat, which points in the direction of my red A vector, and it's length 1. All right, we have a couple properties for vectors. We have this associative property of addition, and that pretty much means that it doesn't matter how you group them. You know, I can do A plus B first and then add C, or I can do A plus B plus C. It doesn't matter like how you group them and add them. The commutative property means that you can swap the order of how you add the vectors, and it doesn't matter. You have the distributive property, and we can distribute this constant alpha into the sum of these two vectors, and it is the same. And then we have finally this associative property of scalar multiplication. Again, similar to the addition one, it doesn't matter how you group them. The multiplication, it comes out the same. Dot product. So say we have our vector A, and it's defined as, you know, how we defined it above. A1 in the I hat direction, A2 in the J hat direction, A3 in the K hat direction. And it's pointing off in that direction. And then we define another vector, B. And remember, take note of the underbar. The underbar tells us it's a vector. And B is defined as B1 in the I hat direction, B2 in the J hat direction, and B3 in the K hat direction. And this points off in that direction. Well, the dot product of A and B, so this is A dotted with B, that's what this is, A dotted with B, is equal to, it's defined as the magnitude of A times the magnitude of B times cosine of the angle between them. And alpha is the angle between these two vectors, you can see here. So that's what the dot product is. We can also write the dot product out in this longer form here. So we have, this is vector A, which we took from here, and then this here is vector B, which we took from here, and we're dotting them, so we have the dot between the two. And then you distribute, right? So we do A1 I hat dotted with B1 I hat, and then we do A1 I hat dotted with B2 J hat, and then we do A1 I hat dotted with B3 K hat, right? And then we would do the same thing for the next term, and then we would do the same thing for the last term. And we'd end up with these 9 terms here. And the important property we want to take away is that a vector dotted with itself is just 1. A vector dotted with another vector that is perpendicular to it is 0, right? So we have I hat dotted with I hat, and I just said a vector dotted with itself is 1, right? So this is 1. I hat dotted with J hat, well, I and J are normal to each other, right? They form a right angle with respect to each other, so this whole term is going to be 0. I hat dotted with K hat, I and K are normal to each other, so this goes to 0, right? And if you go through this all, we'll end up with this term, and this term, right? And that's what we have right here, A1B1 plus A2B2 plus A3B3. So what we really did was we multiplied the components and added them. We multiplied the I hat components, A1 and B1, the J hat components, A2, B2, and the K hat components, A3, B3, and added them. So that's a dot product. That's how we'll take dot products. The dot product is a projection of one vector onto another. I recommend watching this video. The 3 blue 1 brown makes a really cool video with vectors and explaining the dot product and how to get some intuition behind it, and it's really a neat video, so I'd recommend go and watch this and you'll understand what that projection thing means. And here I'm just reiterating that a vector dotted with itself is 1, and a vector dotted with another vector that's perpendicular to it is 0, right? So I hat dotted with I hat is equal to J hat dotted with J hat is equal to K hat dotted with K hat. Those all equal 1. I dotted with J is equal to I dotted with K is equal to J dotted with K, right? And those are all 0 because, you have I and j, and if you dot those, they're normal to each other, which is 0. You know, you can't project anything down onto j or onto I if they're forming right angles with each other, so it's equal to 0. Okay, moving on. We're doing good. Cross product. So if we cross two vectors, we end up with another vector, right? So remember, in a dot product, when we dotted two vectors, we ended up with a scalar. Here in the cross product, we end up with a vector. And the cross product is defined as follows. A crossed with B is equal to the magnitude of A times the magnitude of B times sine of the angle between them, and then multiplied by this unit vector C. And let's explore what this C vector means, this C hat vector. So we have on our right here, we have A pointed in this direction and B pointed in this direction. And then we have the angle between them, which is alpha. And if we take A and B, there's a plane that's formed between A and B, right? And it would be right here. And when we cross A and B, we'll end up with this vector that is perpendicular to this plane. It's perpendicular to both A and B, right? And it points in this direction right here. That is vector C. That's a result of the cross product of A and B. And C hat just tells us, you know, C hat would look like this. You know, it would be of length 1, pointing in the direction of C. Here, if we look here, the dot product is anti-commutative, which means that A cross B is equal to negative B crossed A. So if you flip it, you have to negate it. And then down here is just some right-hand rule stuff. And go to Google and look up, or YouTube or whatever, and look up right-hand rule. There's 1,000 videos, but the essence of it is, let's take this first one. I crossed with j equals k. So you would, and oh boy, I'm gonna forgive my drawing. If you have your hand, so those are the fingers, and then this is your thumb. If you have your hand and you point it along I, and you sweep your fingers into j, that is I crossed with j, and the direction of your thumb tells you, you know, what that's equal to. So I crossed with j is equal to k. So that's what that is. I crossed with j is equal to k. J crossed with k is equal to I. You know, same idea. So you would have your fingers in this plane here. J, oh my gosh. Yeah, J, and then your thumb would point along I, and your fingers would sweep up to K. So J crossed with K is equal to I. Make sure you use your right hand. Left hand, you're going to get the wrong answer. Okay, that was my terrible drawing. This little wheel guy is sometimes helpful. If you do I, J, and K, and you put arrows in a clockwise orientation, then that will tell you, you know, I crossed with J will give you K, J crossed with K will give you I, and K crossed with I will give you J. If you go against the flow of the arrows, say I went I crossed with K, I crossed with K, since I'm going against the flow of the arrows, that will be negative J hat, right? Negative J hat. If I go K crossed with J, I'd get negative I. Okay, so that's how you'd use that. Next, matrix multiplication. This is just your standard matrix multiplication. You take your row and multiply it by your column, row times column, and you add the components, right? So we do A11 times B11, A11 times B11, plus A12 times B21, A12, B21, and then you go on to the next one, row times column, and you do a similar pattern there, and then you go to the next row, so row times column, and then row times column. If you need more examples, you know, just Google it. There's 1,000 examples of matrix multiplication. I know you can get it. We're going to skip the tensor product stuff for now, and we'll come back to it a little later when we start talking about rigid bodies, but I don't think we really need to cover that right now. Derivatives. All right, very important. This is we're going to do this a lot in all of our videos. So let's go over some of the rules we use all the time. So product rule. If you're taking the derivative of the product of two functions, The mnemonic I know is derivative of the first times the second plus the first times the derivative of the second. Right, so f prime times g plus f times g prime. Next one, quotient rule. If you have f equals g over h, and you're taking the derivative of f, then again, another mnemonic, low d high minus high d low all over low squared. Okay. Last one, chain rule. If you're taking the function and there's a function within the function, then what you do is you take the derivative of the outer function and then you multiply that by the derivative of the inner function. And we're going to do some examples. So in dynamics, we often have to perform what's called implicit differentiation. So for example, say we have an angle that is a function of time. So theta of t, it's a function of time. Differentiating this with respect to time would be d theta dt, which is just equal to theta dot. Now this is important because see this aside over here. Say we were taking the derivative with respect to theta, that would just be equal to 1. But because we're taking it with respect to time, and theta is a function of time, this becomes theta dot. Okay, so what if we wanted to differentiate theta of t squared? Well, we'd have to perform the chain rule, right? So we would bring down the 2, multiply it by the inside, 2 theta of t, and then we'd have to take the derivative of the inside, theta dot of t. This is what everyone forgets. This theta dot of t. Don't forget that. You're going to get the wrong answer, and the motion, your dynamics is going to be all over the place, and you're not going to know why, and then I'm going to say because you didn't put the theta of t, theta dot, on the outside. Okay, so don't forget that. I'm going to drop the function of t script for right now and do a few more examples, but just remember that theta is a function of time. I'm just dropping it for clarity. So example number 1. What if we want to take the derivative of sine of theta? Well, we take the derivative of the whole function. So what's the derivative of sine? Cosine. And now we have to take the derivative of what's within sine, which is theta dot. So the derivative of sine theta is theta dot cosine theta. That was an easy one. Let's go to the next one. Number 2, sine squared of theta. So this is really similar to what we did before with this one, theta of t squared, but we're just adding another layer to it with the sine function. So now you'll see what I mean here. So I'm going to rewrite sine of squared and move the squared up here. I think it's maybe a little clearer. So we're going to bring down the 2. So we bring down the 2 here. And then we multiply it by the inside, sine of theta. So now we have 2 sine theta. And now we have to take the derivative of the inside. What's the derivative of sine? Cosine. And now we have to take the derivative of the inside of cosine, which is theta dot. Right? So the derivative of sine theta squared is 2 theta dot sine theta cosine theta. See how there's like another layer to it? We had to go one one level deeper. I feel like Inception or something. Let's go to the next one. Let phi also be a function of time. Okay, so just like theta was theta of t, this is phi of t. So let's take the derivative of theta squared phi. Okay, let's do the product rule. And what was the little mnemonic we learned for product rules? It was derivative of the first times the second plus the first times the derivative of the second. So let's take the derivative of theta squared. Well, we did it up above, right? It's 2 theta theta dot. So derivative of the first times the second. Second is phi, plus the first, theta squared, times the derivative of the second. What's the derivative of phi? Phi dot. All right. Last example. let's take the derivative of sine theta cosine phi. Okay, same thing. Derivative of the first times the second plus the first times the derivative of the second. You're going to be doing that a lot. So derivative of sine is cosine, and then we take the derivative of the inside. That's theta dot. So we have theta dot cosine theta. That's derivative of the first. Times the second, cosine theta. Cosine phi. Cosine phi. And then we do the first, so sine theta, times the derivative of the second. What's the derivative of cosine? Negative phi. Jeez. What's the derivative of cosine? Negative sine. Negative sine. Right, so we have negative sine of phi. And then we have to take the derivative of the inside here, phi dot. Right? So the derivative of sine theta cosine phi is theta dot cosine theta cosine phi minus phi dot sine theta sine phi. All right, calculus. I'm not going to do any calculus. I don't want to embarrass myself. If you know how to do the power rule, U sub and integration by parts, you should be good. We will rarely be taking integrals for the kind of stuff I want to cover. Maybe every now and again we'll do it. But it's going to be mostly those derivatives, those implicit derivatives and everything up top. And again, we'll get a lot of practice doing it. But if you need extra practice on calculus, Patrick JMT is a good one. He has a lot of videos. He helped get me through Calculus 2. Khan Academy is always good. But yeah, that's it. That's the end of this video. So thanks for watching. Go watch the next video. We'll get into some real dynamics soon. Bye.